Nothing sounds like the simplest idea imaginable. It's the word we use when the fridge is empty, when the inbox is quiet, or when a meeting could have been an email. Yet, the moment science takes the word seriously, it starts to misbehave. The closer we look, the more nothing begins to resemble something wearing a clever disguise. This video explores whether nothing ever truly existed, and why modern physics increasingly suggests that it may not be a real state of nature at all. Hello, and welcome to Sleepy Space Traveler. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. Now, let's begin. Most confusion starts with the fact that we casually mix very different meanings of nothing without noticing. In daily life, nothing usually means nothing I was hoping to find. An empty jar on a kitchen counter feels like a good example. You open it, find no cookies, no rice, no screws, and declare it empty. But, of course, it isn't. The jar is full of air, nitrogen, oxygen, trace gases, and a swarm of molecules bouncing around at high speed. If you were small enough, that nothing would feel like standing in a crowded room. So we try again. Suppose we remove the air and create a vacuum. No molecules, no dust, no sound. Now we are closer to what people intuitively mean by nothing. For centuries, even scientists thought of empty space this way: a passive stage where things happen, but which does nothing itself. Modern physics, however, has completely overturned that picture. According to quantum field theory, the framework that underlies all known particle physics, space is not an inert backdrop. Instead, the universe is filled with fields that exist everywhere. Particles are not tiny solid beads. They are excitations of these fields, like ripples on the surface of water. An electron is a ripple in the electron field. A photon, a ripple in the electromagnetic field. The important point is that the water, the field, never goes away. Even when all particles are removed, the fields remain. The state with the lowest possible energy is called the vacuum, but this vacuum is not still. Quantum mechanics forbids perfect calm. Due to uncertainty relations, energy cannot be pinned to an exact value for all time, so it fluctuates. The vacuum seethes gently with temporary activity, brief appearances of particle-antiparticle pairs, and subtle shifts in energy. This is not science fiction. These fluctuations produce measurable effects, such as tiny forces between metal plates placed close together and small changes in atomic energy levels. A useful analogy is the ocean on a calm day. From above, it looks flat and quiet. Look closer, and it is full of motion. Waves, currents, and restless activity beneath the surface. Quantum empty space is like that. Calm by everyday standards, but never truly empty. At this point, some people push the idea further. Fine, they say, empty space is still something. But what if there were no space at all? No distance, no location, no where. This is where imagination starts to struggle. Not because we lack creativity, but because our brains evolved to operate inside space. Remove space entirely, and you can no longer picture a void or a darkness, because those still assume somewhere for the darkness to be. Take away time as well, and things get even stranger. No time means no change, no sequence, no before or after. At this extreme, even the word exist becomes slippery, because existence normally means persisting through time in some place. A timeless, spaceless nothing may not just be unfamiliar. It may be conceptually incoherent. This matters because when people ask whether the universe came from nothing, they often have this extreme version in mind. Yet physics does not clearly describe such a state, and it is not obvious that it could be part of reality at all. These distinctions become crucial when we turn to cosmology. The Big Bang is often imagined as an explosion into an empty void, but this picture is wrong in an important way. The Big Bang was not something that happened in space. It was the expansion of space itself. If you imagine dots drawn on the surface of a balloon, as the balloon inflates, the dots move away from one another, not because they are flying across the surface, but because the surface itself is stretching. In the same way, galaxies recede from each other because space is expanding. When we trace this expansion backward, we reach a state where the universe was extremely hot and dense. But this does not mean all matter was compressed into a point inside a pre-existing emptiness. Space itself was compressed. And because time is part of the same structure, space-time, many physicists think time itself began with this expansion. If that is true, asking what happened before the Big Bang may be like asking what is north of the North Pole. The question sounds sensible, but it assumes a framework that no longer applies. There may not have been a before in the ordinary sense. This does not mean science is claiming the universe popped out of literal nothingness. In fact, many modern ideas do the opposite. Some propose that the universe emerged from a quantum state governed by physical laws, not from philosophical nothing. Others suggest that inflation, a brief period of extremely rapid expansion, occurred before the hot Big Bang phase, driven by a field with its own energy. In such models, the early universe is again not nothing, but something structured and rule-bound. Other approaches replace a beginning with continuity. In bouncing cosmologies, the universe contracts from a previous phase and then rebounds, avoiding a singular start. In some models of eternal inflation, new universes continuously form within an ever-expanding background, so there is no global moment when everything began. In all of these cases, nothing quietly disappears from the story. At this point, it is worth stepping back and asking whether nothing might be more of a language problem than a physical one. Words like darkness and cold feel like things, but they are really absences. Darkness is the absence of light, cold the absence of heat. You cannot collect darkness in a box or pour cold into a cup. Nothing may work the same way. It is a grammatical convenience, a way of saying that none of the things we expected are present. When we elevate that everyday usage into a cosmic concept, we may be stretching the word beyond its limits. Physics, at its most fundamental level, does not seem to include a natural state of absolute nothingness. Even its emptiest states have structure, laws, and potential. The universe appears to resist being truly off. This leads to a provocative reversal of the usual question. Instead of asking why there is something rather than nothing, we might ask why we ever assumed nothing was an option. We have never observed it. Every attempt to strip reality down to zero leaves something behind: fields, geometry, laws, or quantum fluctuations. Perhaps existence is the default, and nothing is the imaginary extreme point our minds invent when we push subtraction too far. None of this settles the question in a final way. It may be that future theories of quantum gravity will reshape our understanding yet again. But the trend is clear. The deeper physics goes, the harder it becomes to find a place where nothing could comfortably exist. If there is a takeaway at this stage, it is not that the mystery has been solved, but that it has been sharpened. Nothing is not a simple starting point waiting patiently at the beginning of time. It is a challenging concept that exposes the limits of intuition, language, and theory. In trying to understand it, we learn more about what the universe actually allows. In the next part, we will dive more deeply into empty space itself and see why modern physics treats the vacuum not as the absence of everything, but as one of the most active and important players in the story of the cosmos. If Part 1 did one important job, it was to remove the illusion that nothing is a simple idea. By the end, we were already suspicious of it. In Part 2, that suspicion turns into a full-blown investigation, because modern physics makes a very strong claim. Even the emptiest space we can imagine is not empty at all. Not metaphorically, not philosophically, physically. This isn't a fringe idea or a speculative guess. It sits at the center of quantum physics, the most successful predictive framework science has ever built. And once you take it seriously, the idea of nothing starts to look less like a possible state of reality and more like a misunderstanding of how reality works. To see why, we need to talk about space itself, and why modern physics no longer treats it as an inert background. For most of human history, space was thought of as a container. Stuff moved around in it, but space itself didn't do anything. It was like the stage of a theater. The actors mattered, the script mattered, but the stage just sat there holding everything up. Even Isaac Newton, whose laws transformed science, imagined space as a fixed, absolute arena where motion took place. That picture began to crack with Einstein, who showed that space and time are dynamic, stretchable, and responsive to matter and energy. But even Einstein still thought that if you removed all matter and radiation, you'd be left with a kind of quiet, empty space-time. Quantum physics shattered that idea completely. In modern physics, the universe is not fundamentally made of particles. That sounds wrong at first, because particles are what we see in detectors, in experiments, in textbooks. But particles are better thought of as events, not ingredients. The real ingredients are fields. A field is something that exists everywhere, even where nothing seems to be happening. Temperature is a field. Air pressure is a field. A magnetic field surrounds a magnet even when nothing is visibly moving. Quantum fields are like that, except they exist everywhere in the universe, even in places where there are no particles at all. There is an electron field, a quark field, a photon field, and so on. Each particle corresponds to a field, and what we call a particle is really a localized vibration of its field, the way a wave on the ocean is a motion of water rather than a separate object sitting on top of it. This changes the meaning of emptiness in a fundamental way. If fields exist everywhere, then removing all particles does not remove the fields. It just leaves them in their lowest energy configuration, a state physicists call the vacuum state. Here is where intuition usually fails. In everyday life, the lowest energy state of something is boring. A ball at the bottom of a hill just sits there. A pendulum eventually stops swinging. A room cools down and becomes still. Zero energy means nothing is happening. Quantum physics refuses to cooperate with that idea. At the quantum level, perfect stillness is forbidden. The rules of quantum mechanics place limits on how precisely certain quantities can be defined at the same time. One of those limits involves energy and time. Roughly speaking, if a system exists for a very short time, its energy can fluctuate. This means that even in the vacuum state, where the average energy is as low as it can be, the energy is not perfectly fixed. It jitters. It fluctuates. It refuses to sit still. A good, everyday analogy is a spring mattress. Even if no one is sitting on it, the mattress is not a rigid slab. It has give. It has flexibility. If you zoomed in far enough, you'd see microscopic vibrations. The quantum vacuum is like that mattress, but built into the fabric of reality itself. These fluctuations are not optional. They are not experimental noise. They are a direct consequence of the structure of quantum theory. And, crucially, they are not just mathematical artifacts. They have physical effects that can be measured. One of the clearest examples is the Casimir effect. If you take two uncharged metal plates and place them extremely close together in a vacuum, something surprising happens. The plates attract each other. There is no electric charge pulling them together. There is no magnetic field. Yet the force is real and measurable. What's happening is that the quantum vacuum between the plates is different from the vacuum outside them. The plates restrict which field vibrations can exist in the gap, and that imbalance produces a pressure that pushes the plates together. In other words, empty space exerts a force. Another example is the Lamb shift, a tiny change in the energy levels of electrons in atoms. Classical physics predicts certain energy levels, but experiments show small deviations. Those deviations are explained by interactions between electrons and vacuum fluctuations. The atom is not sitting in nothing. It is immersed in a restless background that subtly shifts its behavior. There are many more examples: vacuum polarization, spontaneous emission, the Unruh effect, Hawking radiation. Each one tells the same story from a different angle. Empty space is active. It has structure. It participates. At this point, it's important to address a common misconception: the idea of virtual particles popping in and out of existence. This phrase is popular because it's vivid, but it can also be misleading. Virtual particles are not tiny objects that briefly exist and then vanish like fireflies. They are mathematical components of calculations, internal bookkeeping devices used to describe interactions. What matters is not whether virtual particles are real in a literal sense, but that the vacuum behaves as if something is happening, and experiments confirm that behavior. If you don't like the virtual particle picture, you can ignore it entirely and still reach the same conclusion. The quantum vacuum is not nothing. Now, let's connect this to cosmology, because this is where the question of nothing becomes unavoidable. When we look at the universe on the largest scales, we find that it is expanding. Space itself is stretching. Galaxies are moving away from each other not because they are flying through space, but because the space between them is growing. This expansion appears to be accelerating, driven by something we call dark energy. One of the simplest explanations for dark energy is vacuum energy, the energy associated with empty space itself. Here, things get strange in a different way. Quantum field theory predicts that the vacuum should have an enormous energy density. When physicists calculate it, they get a number that is absurdly large, larger than what we observe by about 120 orders of magnitude. That discrepancy is one of the biggest unsolved problems in physics. But notice what this means conceptually. Even when physicists are wildly wrong about the amount, they are still predicting non-zero energy for empty space. Zero does not naturally appear at the equations. This has profound implications. If empty space has energy, then it can influence the dynamics of the universe. It can drive expansion. It can shape cosmic history. In a very real sense, the universe is being pushed around by what we used to call nothing. The early universe makes this even clearer. According to modern cosmology, tiny quantum fluctuations in the early universe were stretched to enormous scales during a period of rapid expansion called inflation. Those fluctuations became the seeds of galaxies, stars, and ultimately planets and people. This is not a metaphor. The small irregularities we see in the cosmic microwave background radiation, the faint afterglow of the early universe, match the statistical patterns predicted by quantum fluctuations. If that sounds abstract, here's a simpler way to think about it. Imagine a perfectly smooth surface of water. Now imagine zooming in with a powerful microscope. You would see ripples, tiny disturbances. Now imagine stretching that surface until those ripples become waves the size of continents. That is essentially what inflation did. It took microscopic quantum jitter and turned it into cosmic structure. Galaxies exist because the early universe was not perfectly smooth, and it was not perfectly smooth because the vacuum itself fluctuates. So when we ask whether nothing ever existed, modern cosmology responds with a quiet but firm answer. The closest thing we have to nothing is deeply involved in making everything. This leads to an uncomfortable realization. The vacuum is not a neutral absence. It is a physical state with properties, dynamics, and consequences. It can push plates together. It can shift atomic energy levels. It can shape the large-scale structure of the universe. Calling it nothing is a historical accident. At this point, some people object. Fine, but that's still space. What about no space at all? That's a fair question, and it points toward the limits of current physics. Quantum field theory assumes space-time exists. It tells us what happens within spacetime, not what happens when spacetime itself is absent. But here's the important point. Every successful physical theory we have replaces nothing with structure. When we try to remove things, we keep uncovering deeper layers rather than arriving at emptiness. Remove matter, you get fields. Remove particles, you get vacuum energy. Remove classical space, you get quantum geometry. Physics does not seem to contain a natural stopping point where nothing appears. Some physicists suspect this is not an accident. They argue that true nothingness may not be a physically meaningful state at all. The laws of quantum mechanics do not naturally allow a state of absolute absence. The lowest energy state is not zero. It is the minimum allowed by the rules. This is very different from how we usually think about nothing. In everyday life, nothing feels like the default. An empty room, a blank page, silence. But even those examples fall apart on closer inspection. Silence is full of air vibrations below our hearing threshold. A blank page is full of fibers, atoms, electromagnetic fields. An empty room is full of air, thermal radiation, and the gravitational pull of Earth. Our intuition for nothing is built from human-scale experiences, not from fundamental physics. And this mismatch matters, because it means that when we ask whether the universe came from nothing, we may be smuggling in assumptions that reality does not share. If empty space is not nothing, and if the vacuum is not nothing, then any model in which the universe comes from the vacuum is not describing creation from nothing in the philosophical sense. It is describing transformation within an existing structure. That does not make such models trivial or uninteresting. On the contrary, they are remarkable, but they do not rescue the idea of absolute nothingness. They quietly eliminate it. There's also a deeper philosophical point lurking here. In physics, absence is almost never absolute. It is always relative to a framework. No particles relative to a field. No excitation relative to a vacuum. No matter relative to space-time. True nothingness would require the absence of the framework itself. And once you remove the framework, it becomes unclear what the statement "nothing exists" even means. You cannot describe a vacuum without space. You cannot describe fluctuation without time. You cannot describe absence without a context in which something could have been present. This suggests that nothing may not be a physical concept at all, but a linguistic one. A word we use when expectations fail. In science, whenever we have tried to formalize nothing, it has turned into something else. A field, a state, a boundary condition, a geometry, something describable, something structured. That doesn't mean physics has answered the deepest questions about existence. It hasn't. But it does mean that the simple picture of a universe emerging from a blank, empty, silent void is increasingly hard to defend. By the time modern physics is finished stripping things away, there's always something left. Not because physicists are afraid of nothing, but because the theories themselves refuse to produce it. In Part 3, we'll turn directly to the Big Bang and the beginning of space-time itself. That's where the question of nothing becomes most tempting and most dangerous, because it's where our everyday ideas about before and after finally stop working. If empty space isn't empty, what happens when space itself begins? And if time has a starting point, what does before even mean? That's where the idea of nothing faces its toughest test yet. By the time we reach the Big Bang, the idea of nothing is already on shaky ground. Empty space isn't empty. The vacuum isn't quiet. Fields, fluctuations, and energy seem impossible to fully erase. But many people still feel that the Big Bang must be the place where nothing finally had its moment. After all, if the universe had a beginning, then surely there was something like nothing before it, right? This is where modern cosmology delivers one of its most counterintuitive messages. The Big Bang was not an event that happened in time, inside space. It was, as far as our best theories can tell, the beginning of both time and space themselves. And once you take that seriously, the phrase "before the Big Bang" starts to unravel in a very uncomfortable way. to understand why, it helps to clear away one of the most persistent mental images in science communication: the Big Bang as a giant explosion. Explosions are familiar. A bomb goes off in a room. Fireworks burst in the sky. A volcano erupts and throws material outward. All of these events have something in common. They happen somewhere. There is a location, a surrounding space, and a timeline in which the explosion occurs. There is a before, a during, and an after. The Big Bang does not fit that pattern. When cosmologists talk about the Big Bang, they are not describing matter exploding into an empty void. They are describing space itself expanding. That may sound like wordplay, but it's a deep physical distinction. A useful analogy is the surface of a balloon. Imagine dots drawn all over it. As the balloon inflates, every dot moves away from every other dot. But none of the dots is flying across the surface. The surface itself is stretching. There is no center on the surface where the expansion began. Every point sees all other points receding. Our universe behaves in the same way. Galaxies are not rushing through space away from a central explosion. Instead, the distances between galaxies increase because the fabric of space is expanding. From any galaxy's point of view, it looks like everything else is moving away, but that does not mean that galaxy is special. The expansion has no center. Now rewind that expansion. As we trace cosmic history backward, galaxies get closer together. Temperatures rise. Matter becomes more compressed. Eventually, we reach a state where the universe was extremely hot, dense, and smooth. This is what we call the early universe, and the extrapolation back toward that state is what leads to the Big Bang. But notice what we are rewinding. Not objects moving through space, but space itself shrinking. And if space is shrinking, time is doing something equally strange. In Einstein's theory of general relativity, space and time are not separate ingredients. They are woven together into a single structure called space-time. You cannot talk about space without time, or time without space, any more than you can talk about length without width on a map. So, if space has a beginning, time likely does too. This is the point where intuition protests loudly. Everything in our daily experience has a before. Breakfast comes before lunch. Childhood comes before adulthood. Even the earliest memories we have sit on top of earlier moments we don't remember. Our brains are built to assume that time stretches infinitely backward. Cosmology challenges that assumption. If time itself began with the Big Bang, then asking what happened before it may be like asking what's north of the North Pole. The question sounds reasonable until you realize that north is defined in terms of Earth's surface. Once you reach the North Pole, the concept stops applying. There is no hidden region beyond it where north continues. You don't fall off the planet. You simply reach a boundary where the coordinate loses meaning. In the same way, before is a time concept. If time begins at the Big Bang, then before the Big Bang is not a time that existed, but a direction that may not exist at all. This does not mean physicists are being evasive or mystical. It means the structure of the theory does not include a temporal dimension beyond that point. Time, as a physical parameter, simply does not extend further back. An analogy that often helps is a video game. Imagine the moment the game starts. Before that, there is no in-game time. Characters aren't waiting around in a frozen state. The game world simply does not exist yet. Asking what the characters were doing before the game started is a category mistake. The timeline only begins once the system is running. From this perspective, the Big Bang is not something that happened at a particular moment in an already existing timeline. It is the moment at which the timeline itself begins. This idea is unsettling because it clashes with our deep-seated belief that every effect must have a cause that comes earlier in time. Cause comes first, effect comes second. That's how the world seems to work. But causality itself depends on time. Without time, the usual notion of cause and effect breaks down. If there is no earlier, then there is no place to put a cause in the way we're used to. This doesn't mean the universe had no explanation. It means the explanation may not look like the kinds of explanations we're used to. Instead of a cause in time, physicists talk about boundary conditions, laws or self-consistent structures that do not rely on something happening beforehand. Evidence for this picture of the Big Bang is strong. The expansion of the universe, first observed through the redshift of galaxies, shows that space itself is stretching. The cosmic microwave background, a faint glow left over from when the universe first became transparent, provides a snapshot of the universe when it was only about 380,000 years old. Its uniformity and tiny fluctuations match predictions made by Big Bang cosmology with remarkable precision. The relative amounts of light elements like hydrogen and helium also line up with calculations of nuclear reactions in an early hot universe. These are not philosophical arguments. They are observational successes. But even with all this evidence, the Big Bang model leaves us with a frustrating gap. When we extrapolate backward far enough, we hit a point where our equations stop working. Densities become infinite. Temperatures blow up. The math breaks. Physicists call this a singularity, and singularities are warning signs. They usually mean that a theory has been pushed beyond its domain of validity. General relativity, powerful as it is, does not include quantum effects, and at extremely small scales and high energies, quantum effects matter. This is why many physicists believe that the Big Bang, as traditionally described, is not the final word on cosmic origins. It may be a signpost pointing toward a deeper theory that we do not yet fully have. Some approaches suggest that the Big Bang was not a sharp beginning, but a transition. In these models, the universe may have existed in some form before the hot expanding phase we observe, but not in a way that looks like ordinary time flowing backward. Time itself may behave differently near this boundary. Other models suggest that time might emerge gradually, the way temperature emerges from the collective motion of particles. Temperature does not exist at the level of a single molecule. It only makes sense when many molecules interact. Time, in some theories of quantum gravity, may work the same way. It may not be fundamental, but emergent, appearing only when the universe reaches a certain level of structure. If that is true, then the question, what happened before the Big Bang, is not just unanswered, it is malformed. It assumes that time is fundamental when it may not be. This brings us back to the idea of nothing. If the Big Bang marks the beginning of space and time, then there was no empty stage waiting for the universe to appear. There was no silent void stretching infinitely into the past. There was no container. There was no nothing in the sense people usually imagine. Instead, there was either a boundary to time, a transition from a different kind of reality, or a regime where our familiar concepts simply do not apply. In every case, nothingness fails to show up as a physical state. Even models that talk about the universe emerging from a quantum vacuum are not describing philosophical nothing. A quantum vacuum has laws. It has structure. It has rules that govern what can fluctuate and how. It is something, even if it is a very minimal something. This is why many cosmologists are careful with their language. When popular explanations say the universe came from nothing, they often mean no classical space and time, or no particles, not absolute absence. The deeper you look, the more qualifications appear. The universe, it seems, does not like being reduced to zero. What makes this particularly striking is that the Big Bang, which is often thought of as the ultimate origin point, may actually be less about creation and more about rearrangement. A change in phase. A shift in how reality behaves. Think about water freezing. At a certain temperature, liquid water becomes solid ice. The molecules don't pop into existence at that moment. The rules governing their motion change. The structure reorganizes. Some physicists think the Big Bang may be similar. Not a moment when something came from nothing, but a moment when reality reorganized itself into a form we recognize as space-time, particles, and energy. If that's the case, then asking what came before the Big Bang may be like asking what ice cubes were doing before the water froze. The answer depends on what you mean by before, and whether the concept even applies. What this means for the original question is subtle but profound. The Big Bang does not provide a clean victory for nothingness. It does not give us a neat moment where the universe emerged from absolute absence. Instead, it pushes us toward a more radical conclusion. Absolute nothing may never have been part of the story at all. Every time physics reaches what looks like an edge, it finds structure instead of emptiness, laws instead of silence, relationships instead of void. This doesn't remove the mystery. If anything, it deepens it. Because if the universe did not come from nothing, then we are left asking a different question. Not, how did something come from nothing, but why does this structure exist at all? That question may not have a final answer. It may be one of those questions that reveals the limits of explanation rather than inviting a solution. But it also reframes our understanding of the cosmos. We are not living in a universe that clawed its way out of nothingness. We are living in a universe that appears to have been structured, constrained, and law-governed all the way down, even at its earliest moments. In the next part, we'll explore what happens when physicists take this seriously and build models where the universe has no absolute beginning at all. Models with bounces, cycles, smooth boundaries, and deeper layers beneath the Big Bang. Each of them, in its own way, quietly removes nothing from the picture once again. And by then, nothing will be starting to feel less like a mystery of the universe and more like a habit of the human mind. By the time we reach this point in the story, nothing is starting to feel like a suspect concept. Empty space isn't empty. The Big Bang isn't an explosion into a void. Time itself may have begun with the universe, making before a slippery word. And now we arrive at an even more radical possibility, one that quietly undermines the original question altogether. What if the universe never came from nothing in any sense? What if something, in one form or another, has always existed? This idea may sound like an escape hatch, but it's not philosophical hand-waving. It emerges naturally from several serious scientific attempts to understand the earliest moments of the cosmos. Each of these models replaces nothing with continuity, structure, or deeper laws. And each one does so not because physicists are uncomfortable with nothingness, but because their equations simply don't lead there. One of the first ideas to push cosmology in this direction is cosmic inflation. Inflation was introduced to solve a set of puzzling features of the universe: why it looks nearly the same in all directions, why space appears geometrically flat, and why certain exotic particles predicted by early theories never show up. The solution was a brief period of extremely rapid expansion very early in cosmic history. But inflation does more than tidy up details. It quietly changes the nature of cosmic beginnings. In many inflationary models, inflation is not a one-time event that starts and stops cleanly. Instead, it's a process that can continue indefinitely in some regions of space while ending in others. Where inflation ends, a universe like ours forms. Where it continues, space keeps expanding at an enormous rate. A helpful analogy is boiling water. Bubbles form in the pot, grow and detach, but the water itself keeps boiling. Each bubble is its own little region, but the process never fully stops. In eternal inflation, universes are like bubbles forming within a larger inflating background. If this picture is correct, then our universe did not emerge from nothing. It emerged from an inflating space-time that was already there. The Big Bang, in this view, is not the beginning of everything. It's the beginning of our region of everything. This immediately reframes the question of origins. Instead of asking why there is something rather than nothing, we're led to ask why inflation exists at all, or whether it must exist given certain physical laws. And notably, inflation itself relies on quantum fields and energy. It is not nothing. It is a highly structured physical process. Eternal inflation also introduces the idea of a multiverse, a collection of many universes with potentially different physical properties. While this idea is controversial and difficult to test, it arises naturally from the mathematics of inflation combined with quantum mechanics. If there are many universes, then our universe's existence does not require a special moment of creation from nothing. It becomes one realization among many, and crucially, there is never a global moment when everything began. Somewhere, inflation is always ongoing. In such a picture, nothingness never gets a foothold. There is always a background process, always some region where space exists and evolves. The universe is not a story with a single opening page. It is more like a book with no first chapter, only endlessly branching narratives. Another approach that removes nothing from the story is the idea of a cosmic bounce. In standard Big Bang cosmology, tracing the universe backward leads to a singularity, a point of infinite density and temperature where known physics breaks down. Many physicists suspect this singularity is not a real feature of the universe, but a sign that our equations are incomplete. When quantum effects are included, especially in approaches like loop quantum cosmology, the singularity can disappear. Instead of collapsing into a point of infinite density, the universe reaches a minimum size and then rebounds, transitioning from contraction to expansion. In this view, the Big Bang is not a beginning, but a turning point. An everyday analogy might help. Imagine compressing a spring. As you push, resistance increases. Eventually, the spring pushes back. Classical physics might let you compress forever in theory, but real materials resist. Quantum geometry, in these models, plays the role of that resistance, preventing total collapse. If the universe bounced, then there was a universe before ours, contracting rather than expanding. That earlier universe may have been very different, or it may have shared some properties with ours. Either way, it means something existed before the Big Bang, not nothing. Some bounce models even allow for repeated cycles, expansions followed by contractions, like a cosmic heartbeat. Each cycle gives rise to a new phase of cosmic history. Time, in this picture, may extend indefinitely into the past and future. This raises difficult questions about entropy and whether information can survive from one cycle to the next, but it offers a compelling alternative to a universe that springs into being from absolute absence. Instead, the universe becomes a long-running process, not a one-off event. Another family of ideas comes from string theory and higher dimensional models. In these frameworks, our universe may be a three-dimensional surface embedded in a higher dimensional space. The Big Bang could correspond to an interaction or collision in that higher dimensional setting. In so-called brain cosmology, universes are like sheets floating in a larger space. When these sheets collide, the energy released can produce conditions similar to the Big Bang. Expansion follows, matter forms, and cosmic history unfolds. Here again, nothingness plays no role. There is a larger arena in which events occur. Our universe's beginning is a local phenomenon, not the absolute beginning of reality. Even more subtle is the Hartle-Hawking no-boundary proposal. In this model, the universe does not begin at a sharp edge in time. Instead, time behaves like a spatial dimension near the origin, smoothly rounding off rather than terminating abruptly. A common analogy is the surface of the Earth. The Earth has a finite area, but it has no edge. You can travel south until you reach the South Pole, but there is no sudden drop-off beyond it. The surface simply curves. In the no-boundary model, the beginning of the universe is like the South Pole of time. There is no earlier moment, but also no singular starting point that demands a cause. The universe is finite but unbounded. This does not mean the universe emerged from nothing. It means that the concept of before does not apply in the way we expect. Time itself is part of the geometry of the universe, not an external parameter. What all these models share is striking. None of them rely on absolute nothingness. Each replaces it with something deeper, an inflating space-time, a previous universe, higher dimensions, quantum geometry, or a smooth boundary in time. In every case, when physicists push their theories as far back as they can go, they do not arrive at a blank void. They arrive at structure. This pattern is not accidental. Physics is a discipline built on relationships, laws, and constraints. Its equations describe how quantities relate to one another. Absolute nothingness, with no structure and no rules, does not easily fit into that framework. In fact, many physicists suspect that absolute nothingness may not be a physically meaningful concept at all. It may be a linguistic idea, born from how humans use negation rather than a state the universe can actually occupy. When we say nothing, we usually mean none of the things we were expecting. No matter in a jar. no sound in a room, no emails in an inbox, but in every case the background remains. The jar exists. The room exists. The inbox exists. When we extend that everyday usage to the universe as a whole, we may be committing a subtle mistake. We imagine removing all the contents without noticing that we are still assuming a container. Modern cosmology keeps removing the container too, and each time it does, the question of nothing becomes harder to formulate. Remove matter and fields remain. Remove particles and vacuum energy remains. Remove classical spacetime and quantum structure remains. Remove time, and the very language of before collapses. At no point do we encounter a stable, well-defined state that deserves the label nothing. This does not mean science has proven that nothing never existed. It means science has so far found no reason to believe it ever did. Every serious attempt to describe the universe's origin replaces nothing with something else, something more abstract, but still something. And perhaps that is the deeper lesson emerging from modern cosmology. The universe may not be a story about how something miraculously emerged from nothing. It may be a story about how complex structures emerge from simpler ones, how order unfolds from underlying rules, how change arises within an ever-present framework. In that sense, the most radical idea may not be that something came from nothing, but that nothing was never an option. This doesn't diminish the mystery. If anything, it deepens it. Because if something has always existed, then the ultimate question shifts. Instead of asking how the universe began, we ask why reality has the structure it does. Why these laws? Why this kind of something rather than another? Those questions may not have final answers, but they are questions that arise naturally once we let go of the idea that the universe had to start from nothing. In the next part, we'll step back from specific models and confront the issue directly. We'll ask whether nothing even makes sense as a concept, whether it is physically possible, logically coherent, or perhaps just a convenient word that breaks down when pushed too far. And by then, it may start to feel less like the universe is hiding something from us, and more like we've been asking it the wrong kind of question all along. By now, a pattern should be impossible to ignore. Every time we push physics hard enough to corner nothing, it slips away. The vacuum turns out to be active. The Big Bang turns out not to be an event inside time. Alternative cosmologies replace beginnings with transitions, bounces, or eternal processes. Even the most radical ideas still smuggle in structure, laws, or possibilities. At some point, it becomes reasonable to ask a more uncomfortable question. What if nothing isn't something the universe can actually do? This is not a mystical claim. It's a practical one. Physics is at heart a rule-based enterprise. It describes what is allowed and what is forbidden. And one of the strangest discoveries of modern science is that absolute absence does not seem to be an allowed state. Let's start with something deceptively simple: language. In everyday speech, nothing feels like a thing. We treat it grammatically like a noun. We say nothing exists, nothing happened, nothing was there. But in practice, nothing almost always means none of the things I expected to find. When you open the fridge and say there's nothing to eat, you don't mean the fridge has vanished into a metaphysical void. You mean there's no food that meets your current standards. The fridge exists. The air inside it exists. the light still comes on. Nothing is a shortcut, not a literal description. The same goes for silence, darkness, emptiness, and cold. Silence isn't a substance. It's the absence of sound above a certain threshold. Darkness isn't a thing. It's the absence of light. Cold isn't an entity. It's lower molecular motion. You can't scoop darkness into a box or pour silence into a cup. These are relational concepts. They only make sense against a background of something else. Nothing works the same way. The problem arises when we take a word that evolved to describe everyday absences and try to promote it into a fundamental feature of reality. We start imagining nothing as if it were a place, a state, or a container that existed before everything else. But this may be a category error. We're treating a linguistic convenience as if it were a physical option. Physics does not naturally include such an option. In quantum field theory, the lowest energy state is not zero activity. It is the minimum allowed by the rules. The vacuum is not chosen arbitrarily. It is enforced. You cannot turn it off without turning off the framework that defines turning off in the first place. Even if you try to imagine removing all fields, you are still left with the mathematical structure that allows you to imagine removal. This is why some physicists say that nothingness is unstable, not in a dramatic sense, but in a logical one. If a system allows fluctuations, then a perfectly empty state cannot persist. If laws exist, then possibilities exist. And if possibilities exist, then nothing is no longer nothing. Think of it like a perfectly flat tabletop. In theory, it could exist. In practice, thermal vibrations, quantum effects, and imperfections make perfect flatness impossible. It's not that flatness is forbidden, it's that it is not a stable configuration. Reality always wiggles. Now zoom that intuition up to the entire universe. If the laws of physics exist at all, then they define what states are allowed. And nowhere in our best theories does a state of absolute nothingness appear as a natural solution. The equations don't point to it. The boundary conditions don't require it. The math doesn't fall into it by accident. In fact, the opposite seems to be true. Something appears to be the default, not nothing. This flips the classic question on its head. We are used to asking, why is there something rather than nothing, as if nothing were the natural baseline and existence needed justification. But what if that assumption is backwards? What if nothing is the strange idea, and something is the inevitable one? After all, we have never observed nothing, not once, not even close. The emptiest regions of space still contain fields. The coldest environments still have energy. Even hypothetical pre-Big Bang states are described using mathematical structures. Nature does not present us with blankness. It presents us with minimal structure, but structure nonetheless. Some philosophers and physicists go further and argue that true nothingness may be logically incoherent. Not just physically unrealized, but conceptually broken. To say there is nothing already assumes a context in which there is has meaning. To talk about the absence of all laws assumes the existence of a meta-law that allows absences. To describe a state with no time assumes a timeless vantage point from which to describe it. It's like trying to imagine a map with no space or a rulebook with no rules. The very act of description reintroduces structure. This doesn't mean all questions about origins dissolve into wordplay. It means we need to be careful about what kind of answers we expect. When physics describes the beginning of the universe, it does not describe creation ex nihilo in the philosophical sense. It describes transitions between regimes, changes in behavior, limits of applicability. Even models that speak of universes tunneling from nothing are using a technical definition of nothing that still includes laws, probabilities, and mathematical relationships. Philosophical nothingness is doing no work there. It has been quietly replaced. Another way to see this is to think about mathematics. Mathematical truths do not seem to require physical existence to be true. The statement 2 + 2 = 4 does not depend on stars, atoms, or time. It does not need a universe to exist to be valid. Some physicists and philosophers argue that the laws of physics may be similar, not inventions, not creations, but features of logical consistency itself. If that's the case, then even before space and time, there may have been structure. Not matter, not energy, but relationships, constraints, possibilities. And once you allow those, nothingness is already gone. This idea is uncomfortable because it challenges a deeply human intuition that existence must start somewhere. But that intuition comes from living inside time. We experience beginnings constantly: birthdays, mornings, first chapters. But the universe does not owe us a narrative arc that mirrors our experience. A book needs a first page. Reality may not. Some cosmological models suggest that time itself is emergent, arising from deeper processes. If time is not fundamental, then asking what happened before the universe is like asking what temperature a single molecule has. The question assumes a level of description that doesn't apply. In that context, nothing is not a missing chapter. It is a mistaken expectation. There's also a psychological component to our fascination with nothing. Nothing feels clean, simple, elegant. It feels like the ultimate explanation. Something from nothing sounds profound, almost magical. It gives the universe a dramatic origin story. But nature is not obligated to be dramatic. Nature is often messy, layered, iterative, and subtle. It builds complexity from minimal rules, not from clean slates. Snowflakes don't emerge from nothing. They emerge from water molecules following simple constraints. Life doesn't emerge from emptiness. It emerges from chemistry operating long enough in the right conditions. The universe may be the same way. Not a miracle pulled from a void, but a structure unfolding from deeper structure. If that's true, then nothingness is not the opposite of existence. It is an abstraction we use when we subtract beyond what reality allows. And that brings us to a quiet but powerful possibility. Maybe there has always been something. Not necessarily stars or fields or even space-time as we know it, but some minimal level of structure, law, or possibility that never needed to begin because beginning itself is a feature that emerges later. This idea appears in many guises: eternal inflation, cyclic cosmologies, quantum gravity models with no initial boundary, mathematical universe hypotheses, even simulation ideas, where computation never truly stops, only spawns new instances. All of them share a common intuition. Existence does not need to be ignited. It is self-sustaining. This doesn't answer every question. In fact, it replaces one deep mystery with another. Why these laws? Why this structure? Why anything at all? But notice how the shape of the mystery changes. we are no longer asking how something broke out of nothing. We are asking why reality has the form it does. That is a subtler question, and possibly a better one. It may also be the kind of question that does not admit a final answer, only deeper descriptions. Physics may explain how one level emerges from another without ever reaching a bottom. Philosophy may clarify what we mean by explanation itself. Neither discipline may ever point to a final because, and that may be okay. One of the lessons running quietly through modern cosmology is humility. The universe is under no obligation to conform to our intuitions about beginnings, causes, or simplicity. Our concepts evolved to help us survive, not to decode ultimate reality. When those concepts fail, the failure is instructive. The idea of nothing may be one of those failures, not because it is useless, but because it reveals the limits of how we think. It shows us where language blurs, where intuition misleads, and where the universe refuses to provide the kind of answer we were hoping for. And yet, the question remains valuable. Asking whether nothing ever truly existed forces us to examine what we mean by existence. It sharpens our understanding of space, time, causality, and law. It pushes physics to clarify its foundations and philosophy to confront its assumptions. Even if the answer turns out to be nothing was never an option, the journey to that answer teaches us something profound. The universe is not balanced on the edge of non-existence. It is robust, structured, and stubbornly present. Reality does not flicker uncertainly between being and nothingness. It behaves like something that expects to exist. In the final part, we'll step back from models and arguments and ask what this all means for us. Not just for cosmology, but for how we understand our place in a universe that may never have emerged from nothing at all. A universe that may have always been quietly, persistently, and improbably here. And that, in its own way, may be the most remarkable conclusion of all. At some point in every long investigation, there's a moment when you stop digging for new layers and start asking what the digging itself has revealed. That's where we are now. After quantum vacuums that refuse to stay quiet, big bangs that aren't explosions, universes that bounce, inflate, branch, collide, or smooth themselves gently into existence, and philosophical arguments that question whether nothing even makes sense as an idea, one thing has become clear. The universe does not seem especially interested in giving nothing a starring role. Instead, what keeps showing up is structure. Sometimes that structure is familiar, like particles and forces. Sometimes it's abstract, like quantum fields, space-time geometry, or mathematical relationships. Sometimes it's deeply speculative, like higher dimensions or eternal inflation. But in every serious attempt to understand cosmic origins, nothingness either evaporates or turns out to be something else in disguise. This isn't because scientists secretly dislike nothing. It's because physics, as a discipline, works by describing relationships. And absolute nothingness has no relationships to describe, no properties, no behavior, no rules. Once you try to give it any of those, it stops being nothing. That realization subtly shifts the original question. Did nothing ever truly exist? Starts to feel less like a historical inquiry and more like a test of our assumptions. We often ask the question as if nothing were the natural starting point and existence were the surprising thing that needs explaining. But the universe seems to be telling us the opposite story. Existence looks stubborn, persistent, hard to get rid of. Even the emptiest possible states allowed by our best theories are still states. They still obey laws, they still have structure, they still allow change, fluctuation, or emergence. Nature does not seem to include an off switch. This is deeply unintuitive, and that's okay. Human intuition evolved to handle ripe fruit, social alliances, and predators hiding in tall grass. It did not evolve to reason about the absence of space-time or the behavior of quantum fields at the Planck scale. When our intuitions fail here, that's not a flaw in us. It's a reminder of how far we've pushed beyond our natural habitat. What makes this journey interesting is not that it produces a final answer. It's that it changes how we think about the problem. Early on, the question feels binary. Either there was something, or there was nothing. By the end, that framing feels crude. The universe doesn't divide neatly into something and nothing. It divides into layers of description, each with its own rules and limits. At one layer, we talk about particles. At another, fields. At another, space-time. At another, quantum geometry. And beneath all of them, possibly mathematics, logic, or structure that doesn't live in space or time at all. At no layer does absolute absence appear as a stable option. This leads to a conclusion that is subtle but powerful. The question of nothing may not be a question about the universe, but about us. We are the ones who imagine nothing as a possibility. We are the ones who picture a blank slate and ask why it wasn't left blank. But the universe, as far as we can tell, does not share that imagination. It behaves as if something is the default, not the exception. That doesn't mean the universe is simple. Far from it. It means that complexity does not emerge from emptiness, but from constraint. Laws limit what can happen, and within those limits, astonishing variety appears. Galaxies form not because the universe had everything available, but because it had very specific rules. Life emerges not because matter can do anything, but because it can do just enough. Seen this way, the absence of nothingness is not disappointing. It's reassuring. It suggests that existence is not balanced precariously on the edge of non-existence. It is grounded, stable, deeply lawful, even when we don't yet understand the laws. There's also a quiet emotional shift that comes with this perspective, even if we don't usually talk about emotions in cosmology. If the universe did not come from nothing, if it did not teeter into being by accident from an absolute void, then existence feels less fragile. Not in a cosmic importance way, but in a grounding way. Reality is not a fluke clinging to the edge of oblivion. It is a process that seems comfortable with itself. That doesn't make human life less special. It makes it more interesting. We are not rare because we exist in a universe that almost wasn't. We are rare because we exist in a universe that is vast, structured, and old enough to produce beings capable of asking questions about nothing at all. We are local patterns in a much larger order, patterns that can reflect on the whole. In that sense, asking whether nothing ever existed is not a distraction from real life. It's one of the ways real life becomes visible against a larger backdrop. When you zoom out far enough to ask these questions, everyday concerns don't disappear, but they change scale. They stop feeling like the entire story. there's also a kind of humility baked into this conclusion. After everything science has learned, after centuries of increasingly precise models, we still don't know whether the universe had a beginning in the deepest sense. We don't know whether time is fundamental or emergent. We don't know whether reality is finite or eternal, singular or multiversal, computed or continuous. What we do know is that nothingness has not shown up as a useful explanation. That's an important negative result. In science, ruling things out is often as valuable as confirming them. We may not know what lies at the deepest level of reality, but we have strong reasons to suspect it isn't nothing in the way we casually imagine it. And that leaves us with a strangely satisfying ending. Not a solved mystery, but a clarified one. If nothing ever truly existed, it left no trace. No theory requires it. No observation points to it. No equation seems to miss it. And if it never existed, that doesn't make the universe less mysterious. It makes it more coherent. The universe may not be a story about something emerging from nothing. It may be a story about something transforming into more something, guided by rules that never needed to begin. A story without a first page, but with endlessly unfolding chapters. And here we are, one of those chapters, made of atoms that were once starlight, governed by laws older than stars, asking questions that stretch language to its limits. That, perhaps, is the final irony. We ask whether nothing ever existed, and in doing so, we reveal just how much there is to think about. Not knowing the answer is not a failure. It's an invitation. Because in a universe where even nothing turns out to be something, curiosity may be the most fundamental thing of all.